Okay, let's dive into something pretty fundamental for 3D printing functional parts. We all love the promise of additive manufacturing, right?
Absolutely. Creating these incredibly complex shapes fast without all the expensive tooling.
Yeah. But what happens when those complex shapes actually have to work,
Right.
in the real world?
Right.
Think about like a lightweight gear or maybe a drone propeller, even a component in a robotic arm.
Mm-hmm. Things that move, things that experience forces.
Exactly. How it handles stress and, crucially, how it handles vibration, that becomes absolutely critical.
And vibration, it's not just, a minor annoyance. It really impacts performance, the lifespan of the part.
Yeah.
And it can even cause catastrophic failure if the part hits resonance.
Resonance, right? That specific frequency where it just vibrates uncontrollably.
Exactly. So controlling that vibration, it's essential for engineering.
And the source material for this deep dive is a research paper that really zeroes in on this exact challenge for a very popular 3D printing material, PA6.
PA6, yeah, commonly known as nylon 6. It's a real workhorse thermoplastic.
You see it a lot in fused filament fabrication, FFF.
Definitely. That's your standard, desktop extrusion printing. PA6 is valued for its strength, its durability.
So this specific study, it takes a really interesting approach. It looks at how three key things influence the vibration behavior of these printed PA6 plates.
Okay, what are they?
How you actually layer the material using different densities, the overall amount of material packed in the infill percentage,
Right, the infill.
and even how the finished part is held or mounted. Its boundary conditions.
Ah, boundary conditions. Yeah, that's crucial. So they're treating these FFF parts almost like layered structures, kind of like composites.
That's the idea, yeah.
That's a clever way to analyze them. And the authors mentioned this is actually the first study of its kind to specifically combine these factors, the layering, the infill distribution, and the boundary conditions for PA6.
So our mission for this deep dive, let's unpack this paper, pull out the core insights. We want to understand not just what printing and design choices affect vibration, but really get to the why behind it.
Sounds good. So to set the stage, the paper first looked at the baseline material properties.
Okay.
They used standard PA6 filament. It's a semi-crystalline nylon. Like any material, its fundamental properties dictate a lot about how it behaves.
And they started by testing how the printed material actually behaved under load, right? Looking at things like strength and stiffness based on how much plastic they packed in.
Exactly. They printed test samples with different infill percentages, 40%, 70%, and 100%.
Okay.
And they used a hexagonal infill pattern. Their tensile tests confirmed what you'd generally expect.
There too.
Higher infill significantly increased the material's strength and its stiffness. That's its elastic modulus.
Right. So basically more plastic packed in means a stronger, stiffer part. Makes sense.
Precisely. They saw a clear boost in both tensile strength and the modulus as they went from 40% up to 100% infill.
And density went up too, obviously.
Density also increased directly with infill. Yeah, I mean, you're packing in more actual polymer material, fewer air gaps.
Okay, and connecting that back to vibration, why is that relationship between the infill, the stiffness, and the mass so important here?
Well, because stiffness and mass are two of the primary factors that determine an object's natural frequencies.
The frequencies it likes to vibrate at.
Exactly. Generally speaking, the stiffer something is, the higher its natural frequencies will be. And the more massive it is, the lower its natural frequencies will be.
Right. More mass, harder to get moving quickly.
Sort of, yeah. So understanding how infill affects these properties, stiffness and mass, is really foundational for predicting vibration.
Got it. So they established that infill gives you this lever to control stiffness and mass. Then they moved on to the vibration analysis itself. How did they simulate or test that?
They used a simulation method called the finite element method, or FEM.
FEM, okay.
Yeah, using ANSYS software. You can think of it like breaking the plate down into thousands of tiny pieces mathematically and calculating how they all interact when vibrated.
So it's a computer model predicting behavior.
Right. It's a standard, very powerful technique for predicting structural behavior. They used a specific element type, shell 281, good for thin structures.
And they had to make some assumptions about the material properties for the simulation, like treating it as uniform.
Yes, they assumed the material was isotropic.
Meaning its properties are the same in all directions.
Correct.
Right.
Now, while 3D prints can show some directional differences, because of the layering.
Anisotropy.
Right. But the authors justify this approximation as pretty common because for thin parts like these plates, the elastic modulus, which is significantly impacted by the infill.
Stiffness factor we talked about.
Exactly. That's the most critical factor influencing the natural frequency. So focusing on that gives a good prediction.
And did they check their model? Validate it?
Oh, absolutely. You have to. They compared their simulation results to existing studies for similar plate and beam types,
Yeah.
showed good agreement. So that confirms the model is reliable for these kinds of predictions.
Okay, good. So they've characterized the material, printed samples with controlled parameters, set up a reliable simulation. What were the specific variables they then explored in the vibration analysis?
So they focused on calculating the first 4 natural frequencies for these PA6 plates. They looked at plates made of 3 distinct layers.
3 layers, okay.
Each layer was the same thickness, 0.001 meters, and the total length was kept constant. The real key variable here was how they stacked the different infill percentages, 40, 70, 100% within those 3 layers.
Ah, so not just using one infill percentage throughout the whole part, but actually mixing and matching them layer by layer, like a sandwich.
Precisely. They tested 9 different stacking configurations.
9? Wow.
Yeah, everything from, solid 40, 40, 40, or 100, 100, 100, all the way to mixed layers like, say, 40, 70, 40, or even 100, 40, 100.
Okay, interesting combinations.
And they also varied the plate's aspect ratio. That's the length relative to the width. They tested ratios of 1, 1.52, and 2.5.
So different shapes from square to more rectangular.
Right. And one more thing. They considered 2 different ways the plate could be held or constrained.
The boundary conditions you mentioned earlier.
Exactly. Fully clamped on all edges. Think of holding it rigidly all around, called CCCC, or simply supported on all edges, SSS, where the edges can rest on supports but are free to rotate slightly.
Got it. So 9 layered recipes, 4 different shapes, and 2 ways of holding the part. That's a lot of combinations. What did they find was the most impactful factor?
Well, the stacking sequence of the infill layers, how they arranged those 40, 70, 100% layers, turned out to be incredibly influential.
Okay.
And in some ways, the results were quite surprising.
Okay, here's where it gets really interesting. What was the big surprise? Lay it on us.
All right, so the configuration that consistently produced the highest natural frequencies, it wasn't the one with the most material overall, the 100, 100, 100. It was the one with 100% infill layers on the top and bottom surfaces and only 40% infill in the core.
The 140-100 configuration.
That's the one. And conversely, placing the dense 100% infill layer in the core with lighter 40% infill on the surfaces.
A 40-140 setup.
Yes. That generally resulted in the lowest natural frequencies.
Whoa, okay, that feels completely counterintuitive.
No.
You'd naturally think packing more material, especially into the core, would make it stiffer and increase the frequency, or at least that the solid 100% one would be highest. What's the why behind this?
It really comes down to this interplay between stiffness and mass distribution, particularly how it affects the plate's ability to resist bending its flexural rigidity.
Okay.
So when you place those stiff, high infill 100% layers on the surface, they're furthest away from the neutral bending axis, the center plane.
Right.
They become incredibly effective at resisting bending, like an I-beam where the flanges do most of the work.
Okay, I see the analogy.
So this significant boost in structural stiffness, in flexural rigidity, it has a more dominant effect on raising the natural frequency than the overall mass of the part does.
So stiffness on the outside wins for higher frequencies.
For raising natural frequencies in these bending modes, yes, it seems so in this study. Now, if you put the dense high infill layer in the core, like in that 140 setup, you add a lot of mass right there in the middle. And while that layer does add some stiffness to the core, the increase in mass has a more significant impact, tending to lower the natural frequencies.
Especially for vibration modes where the center moves a lot.
Exactly. Especially for modes where the center of the plate is experiencing large displacements. So it's this clear trade-off. Surface stiffness dramatically boosts rigidity, while core mass primarily adds inertia, which lowers frequency.
Fascinating. So it's not just about the total amount of plastic you use, but really about how you engineer its distribution through the layers. That's clever. What about the simpler case where all the layers were the same infill?
Right. When all 3 layers had uniform infill, the 40, 40, 40, 70, 70, 70, or 100, 100, 100 cases, The frequencies behaved more, let's say, intuitively.
Oh, so?
The 100% uniform infill gave the highest natural frequencies, followed by 70%, then 40%.
Okay, that makes sense. More solid overall is stiffer.
Exactly. In that scenario, the increase in stiffness from uniformly adding material just dominates over the uniform increase in mass.
Right, and what if they kept the surface layers the same but just varied the core?
Yeah.
Like a 40x40 where x is 40, 70, or 100.
Good question. In that case, increasing the core infill from 40% up to 100% in that 40x40 setup actually decreased the natural frequencies.
You decrease, so putting more material in the middle lower the frequency.
Yes. Again, in that specific configuration, adding mass to the core layer dominated over the stiffness gain in that position.
Okay, and the opposite. Varying the surface layers with a constant core, like x40x.
The opposite trend, just as you'd expect now. Increasing the surface infill from 40% to 100% with that constant 40% core, it increased the natural frequencies.
Because those stiffer outer layers provided that critical boost in flexural rigidity.
You got it.
Okay, so stacking sequence is clearly a major lever you can pull.
Mm.
What else did they find? Did the aspect ratio matter much?
Yes, increasing the aspect ratio, making the plate longer relative to its width, also generally increased the natural frequencies.
Why is that?
It's largely due to increased structural stiffness in that longitudinal direction as the plate geometry changes and gets longer.
Makes sense. And how about how you hold the part, the boundary conditions?
Yeah.
Did that matter as much as how you printed it?
Oh, absolutely. It made a huge difference. Plates that were fully clamped on all edges, the CCCC condition.
Held rigidly.
Right. They had significantly higher natural frequencies compared to those that were just simply supported, the SSS condition.
How significant was that difference? Like, ballpark.
Well, let's take that simplest configuration, the 40-40-40 plate with an aspect ratio of 1, so it's square plate.
Okay.
Its first natural frequency under fully clamped conditions was around 80 hertz.
80 hertz, okay.
But under simply supported conditions, it was only about 44 hertz.
Wow. That's nearly double the frequency just by changing how the part is mounted or constrained.
It is. Those clamped edges provide much greater resistance to movement and flexing, making the whole structure effectively much stiffer.
Right. So if you're out there designing a functional PA6 part where vibration is really critical, maybe it's for noise reduction or avoiding that dangerous resonance, or just ensuring durability, these findings give you real practical control. You can actually tune its vibration behavior, not just by printing with more or less plastic overall, but strategically by how you distribute that material in layers.
The stacking sequence.
And by seriously considering how the part will actually be mounted or fixed in place.
Yeah, it moves beyond just printing a cool shape to actually engineering its dynamic response based on both its internal structure and its external constraints.
So, okay, let's summarize. This deep dive really confirms that for these 3D printed PA6 layered plates, the vibration characteristics are, well, complex, but they're also predictable. They result from this interplay of the stacking sequence of the infill, the aspect ratio of the part, and crucially those boundary conditions.
And I think the key takeaway, the really impactful finding, is how that distribution of stiffness and mass within the layers works, especially the contribution of those stiff surface layers to flexural rigidity versus the mass contribution of the core layer.
Yeah, that 100-4100 being highest frequency and 4140 being lowest, that really drives the point home.
Exactly. Putting stiff material on the outside is powerful for increasing frequencies, while putting dense material in the core can actually lower them depending on the mode shape.
So these results, they provide really valuable, actionable guidance for designers and engineers using FFF.
Definitely. You now know you have specific parameters within the printing process itself, not just overall infill percentage, but how you layer it, and also external factors like mounting that you can leverage.
Leverage to tune the natural frequencies of your PA6 parts.
To get better performance, better lifespan, better efficiency in their real-world applications, it opens up exciting possibilities for optimizing printed parts beyond just their static strength or weight.
It really does. You know, this study shows us how layering different densities of the same material affects how a part vibrates. It makes you think.
What's next?
Yeah. What if we could take this a step further? What if future printers let us layer not just different infill densities, but actually print and layer different materials? Maybe materials with unique vibration damping properties or extreme stiffness, all within the same print job.
Multi-material printing for dynamic tuning.
Exactly. How much more incredible control could we potentially gain over the dynamic response of 3D printed structures then?
That's a fascinating thought to explore.